Yeah, I cannot hear what Krishna is saying, although Gaurav's voice was very clear. Hello?
Yeah.
Yeah, I cannot hear Krishna's voice at all. Gaurav's
Okay.
voice, yeah.
Maybe I have muted it. Okay. Now you'll be able to.
Can you hear now?
I can hear, but your writing is very, very light. So you can make it, press a little more perhaps. I cannot read, it is very light.
Red pen, can I try red pen? Can you see this?
No, 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 no.
Okay,
Maybe completely black.
okay, then what can we do?
Black.
This is an experiment, so let's, we have not tried into the blackboard and Zoom and all that.
If we change these lights, zoom in a little bit.
Does this work?
So this is slightly better here. Yeah, this will do. Yeah.
Is it better?
Yeah, yeah, yeah.
Okay. No, it's not that. It is simply the lighting and so on. It's not that. It's not. No, the blackboard is not. Okay, let me try to write it harder. So this is a matrix. If you reflect it along the diagonal, and if it doesn't change, it's called symmetric. If all the entries are real and the matrix is symmetric, then you look at what are called eigenvalues, namely solutions of this matrix. If I call this matrix as A, then AU equals some number lambda U. We have solutions for these, and all the solutions where lambda is a number are all real numbers. So you'll have typically n solutions for n cross n matrix. These numbers are all real, because matrix is symmetric and real entries. And this is one way of producing these numbers. Another way of producing these numbers is look at the determinant of A, this matrix minus identity times lambda. This is a polynomial of degree n. Then all the zeros of Pn is precisely the same. So there are two ways of getting these numbers. They are called the eigenvalues. So these are called eigenvalues. Eigenvalues of the matrix. This all of us know from linear algebra. So what are we going to do today? We are going to talk about matrices that are not just real entries, but random variables. V1, 1 omega, and so on, V1 n omega, Vn n omega. And because this is a symmetric matrix, all the things that are here are just reflections of those. And what I'm going to consider is these matrices where V1j, Vij omega, this collection are independent and identically distributed random variables. Of course, they're all real values. So I'm going to consider real valued random variables as entries of this matrix. Okay, we'll call it Hn. H sub n omega. Right? These are called random matrices. So as omega varies in a sample space, omega, look at for every pair ij in this set, look at the random variable Vij from omega to r, and look at this matrix formed out of those. Such a thing is called a random matrix. So if you fix a parameter omega, then clearly such a matrix will have, by that thing that we said, will have eigenvalues lambda 1 omega and so on, lambda n omega. Okay, these are the eigenvalues of such a matrix. These are themselves random variables.
Sorry,
Krishna, very basic.
Yeah,
The random variable is a function.
is a function,
Measurable function.
measurable function. That's all. A random variable is a measurable function. A random variable,
And by omega, you are meaning its evaluation at omega.
yeah, is a measurable function. From omega to r. And omega is a point in omega. So if the function is f at omega is this. Actually, the confusion here is because mathematician writes a function as f, physicist writes a function as f of omega. Its evaluation at a point as a function, right? Same thing happens here. I should have written Bij as a function, as a random variable, but you put a parameter because you follow the physics. So one has to, exactly like when we say f of x is a function or f is a function. So if you are a very precise mathematician, you say f is a function. Otherwise, loosely you say f of x. So that is the confusion here. So for every parameter omega, once you evaluate the random variable at that point, you get a matrix. So that is the random matrix. And you have the eigenvalues. So this is a matrix called, this matrix is typically called Wigner matrix. Because originally this was formulated by Wigner to describe the spectra of large atoms. See, we all are used to solving the hydrogen atom or whatever in quantum mechanics, maybe helium or maybe more. But if you go to larger and larger matrix of atoms, then getting mathematical spectrum is not an easy thing. So Wigner proposed that for large atoms, the eigenvalues behave almost like the eigenvalues of a collection of matrices like this, in the limit as n goes to infinity. So one is actually interested in random matrix theory, such matrices in the limit as n goes to infinity. So we are interested in very large n random matrices. So this is something we have to keep in mind.
It would depend on the measure also, right? Like
Yeah.
what distribution you are starting with on omega.
Yeah, there are some universality theorems, I'll tell you in a moment.
And this independent, whatever, does it amount to saying that the determinant is non-zero for this matrix? Yeah,
Almost everywhere you will have
almost.
matrices.
That's equivalent to this.
It's not equivalent, but you will have based on the distributions, right? So I'm not sure if it is equivalent, but I'm sure almost everywhere it is. Actually, spectrum also turns out to be simple, so it's because of that. So anyway, so these are the random matrices. This is called a Wigner matrix. So Wigner formulated this long ago, and then there are some quantities that are related to this that give you both qualitative and quantitative information about the spectra. That is, spectrum means the eigenvalue collection of these matrices. So one such is the following. Let me write here. So one such is, if you have, and actually one doesn't take this matrix itself. What one does is one normalizes this. So one normalizes the random variables as follows. Take Bij omega such that the expectation of Bij omega of 0 for every pair Ij, and the variance is 1 for all of them. And then one normalizes this matrix by a square root of n. So that if I take the variances of a row sum, it is 0. Rho sum is 0, expectation, and the variance of the norm of square of a row is 1 by this normalization. Okay. So what it does is for large n, essentially all the eigenvalues, this collection is essentially in -1, 2 because of this normalization. Essentially means there are very small numbers outside. Okay. So given this, the question that one asks is the following: some simple objects, simple quantities that are related to this matrix. So question 1, what is the function? So look at, I'll denote this set of eigenvalues, lambda 1, omega, etc., lambda n, omega as sigma of h sub n of omega. I'll denote it like this. Then the first question is, if I count the eigenvalues inside an interval AB, we know that the total number is n, clearly, is n cross n matrix. Suppose I take small interval in -2 to 2 and ask how many eigenvalues are there. This is some number smaller than or equal to n, and then we divide it by n, then this is a number between 1 and 0. So always for every n. For every n, it is a number between 0 and 1. So the question is, what is the limit of this? N going to infinity of this. That is the first question. How does it behave? Okay. So the answer to this is the famous Wigner's semicircle law, for which, of course, we need to know how these random variables are distributed. So let me assume here, so assume that Vij of omega are distributed like normal 0, 1. That means the probability that Vij of omega is in an interval CD is e to the minus x squared by 2 integral c to d dx by 2 pi. So that's what the probability is. That's what normal 0, 1 is. So let us assume that for every pair ij, this happens. Then the answer is that this limit is given by an integral a to b 2 by pi square root of 1 minus x squared by 4 dx. Okay, and this is the famous Wigner semicircle law. So this is what was proved by Wigner long ago for Gaussian random variables.
So
Now-
independence is not needed for this
Which independence?
of the outline.
Of course, all these are independent. It's always assumed that all the n into n plus 1 random variables in the upper triangular part are all independent and identically distributed. And the common distribution is normal 0. That assumption is always there in the background. Okay. So this is what is shown, that this measure converges to the semicircle measure. Okay. Now the universality statement is that This is true even for a large class of distributions mu, namely, if I replace normal 0, 1 by any other measure, the exact conditions I don't remember, but a huge class, essentially any probability distribution, which is absolutely continuous, should do. For all of them, this law holds. So that's what he said, universality statement. That is independent of what distribution you take. It's like the central limit theorem. In the central limit theorem, when you take some of random variables, appropriately normalized, independent and magnetically distributed, mean 0, then they all converge to the normal 0, 1, independent of which distribution individual is. So the same kind of universality is here. This is a beautiful thing. Now, not only for these matrices, but for other collections of matrices, namely, instead of taking this, suppose I cut it off after some stage and take a band matrix, 0 here and 0 there, where the bandwidth is W, 2W, let us say, 2W plus 1. You take a band of entries around the diagonal and call this H sub n, comma W, and you normalize W instead of n, you take W, square root of W here. Then such a matrix is called a random band matrix. Okay, this is called random band matrix. Random band matrix. So if I take random band matrices with again similar assumptions, you take the upper triangular part, which is non-zero, to consist of independent and identically distributed random variables. Symmetric random variables are real valued. Then form the same quantity for Hn, W, and ask this question, the limit is again the same. Okay, this was shown by this semicircle law for random band matrices. When I have the condition that W is like n to the power some alpha, n, I keep writing the capital N. So n to the power alpha, where alpha is between 1 and 0. I take this so that the band is increasing with size of the matrix at some rate. Okay, n to the half is like much smaller than the size of the matrix. So when you take this, the same law holds, the same n here, because the total number of eigenvalues are still going to be n. Even though the bandwidth is W, the total number of eigenvalues is going to be n. Therefore, you take the normalized counting function on the set of eigenvalues. That's a function between 0 and 1. So in the limit as n goes to infinity, you get the same thing. This was shown by Marchenko, Molchanov, Pastur, and Khorunzi. These people showed this again for a large class of distributions that the entries are subjected. Again, there is a universality independent of the initial distribution. We still have the same.
What do you interpret this limiting? Does it come in other places?
Semicircle law.
There's no cultural.
No, there is, I mean, you can always write a fractional theorem just with any measure. Take L2 of that and write, but that
Some
doesn't.
semicircle do that.
I'm not sure. I mean, I don't know. maybe there is.
So the band is not very flat. That's the
Sorry?
band should not be very flat. That's it.
No restriction. It can be any band. You can go all the way to 1. No restriction on the band. See, Wigner's theorem means that alpha equal to 1. But this theorem says that you can even restrict it to smaller bands, even then it is.
If you take diagonal, it will be equidistributed with respect to 0.
If you take the diagonal, it is just you'll have independent entries.
So it will be equidistributed.
You will get you should get a counting function to be possible. Because independent random variables. Yeah, you had it.
So mine was, I'm not sure if it is related or not. So here you're getting integrals over a circle. Can you change the problem so that it gives integrals over ellipses?
No. This measure, it's like the Gaussian measure for central limit. Think of it like that. There is a stable region for the limit, and this semicircle lies like the Gaussian theorem. This is like something like central limit theorem, you should think. Of course, for this Wigner case, there is alternative proofs using free probability, where also this proof is given. I'm not sure if it exists for random band matrices. So this is the statement. So what this says is that roughly, if I take this interval -2 to 2, if I take this interval, because the limiting probability has density like this, which is positive, then around every point E, there are infinitely many eigenvalues. So in a sense, what it says that every point E is a limit point of eigenvalues. Firstly, as n goes to infinity, you have infinitely many eigenvalues in a bounded -2 to 2, right? So they'll have accumulation points, limit points. So the limit points could be this cluster. But what this is telling you, that the density is positive around every point, tells you that every point is a limit of eigenvalues. Okay? Every point is a limit point of eigenvalues. So this is a relatively simple question like the central limit theorem. So the next question that one is interested in is the following. So let me erase all this and just keep this matrix and various things associated with in mind. And just keep in mind what I said, that every point in -2 to 2 in the limit has infinitely many eigenvalues around it. Every point in any neighborhood.
Sorry. So by eigenvalues, you mean every one of these lambda i's are functions. So do you mean
So take union of sigma of Hn W of omega as n goes to 100. This is subset of -2 to 2, roughly speaking, almost every omega. Okay, so almost every omega, this is subset of -2 to 2. There are infinitely many numbers. And you would think that the limit points are some clustered thing, but not. Every point is a limit. Okay, so that the closure of this set is -2 to 2 closed interval. That's what it's saying. So when that happens, what one is interested in is the question, what is the local behavior? Eigenvalues. That is, I have -2 to 2. Suppose I take a point E here, and I take an interval then how do the eigenvalues behave locally and what is the counting function there and how does it behave? If you ask this question in the limit, every quantity will go to infinity here. Any counting function of any positive interval of positive length will go to infinity, clearly. Right? So one has to ask the right question. So what is the right question? The right question is, you keep track of n, and at every stage you look at a different interval. So you have this matrix lambda n, and you have eigenvalues for every omega, lambda n, omega are there. So if you look at an interval here, E, and suppose I partition this into lengths of size intervals equal number of intervals of size 1 by n, then since there are totally n eigenvalues, and so roughly you can expect, because they're all over the place, you can expect that every interval will have maybe 1 or 2 finitely many. Or if I take any finitely many of them, here you will have finitely many. So take an interval AB here. Then at this stage n, there are finitely many numbers. So what I'm going to do is, for every n around a point E, I am going to take an interval AB and divide it by n. Okay. So as the matrix size increases, there are more and more eigenvalues that will pile up at E. But then if I also shrink the region where I am looking, you will still catch only finitely many, not too many. Okay. So that's what is one going to do. And therefore, what one is going to look at the counting function, number of points of the eigenvalues of h and w of omega in the interval E minus a by n to E plus a by n, when E is a point in minus 2 to 2. I'm taking the open interval, but it doesn't. I mean, the endpoints are not nice, so I just take here. So I will take this counting function. I don't normalize it because I know that there are only finitely many. I expect there to be finitely many. Now this is a function. This function, if I call this, say, n sub n of an interval AB, if I call this
P anymore, minus x.
minus AB. Right. Actually, I should take AB. So I take this, I'll call this function n sub n because it depends on n, and it depends on parameter omega of this interval AB. Okay, I take an interval AB around in R in the real line, and I count this.
Doesn't depend on me.
Doesn't depend on?
The point
So it depends on E. Thanks. So NE of this. I'm going to fix E once and for all. So if I look at this function, then actually what I have written is wrong. This is what it is. This is nothing but this interval is E plus 1 by n AB. That's what I want. Okay. Gaurav, sorry, I keep reducing the size. Is it okay? Size of the letters?
Well, people are saying keep it as big as possible, but
Okay.
yeah.
E plus AB by n. That's what it is.
Yeah.
So if I look at that function, then it's a counting function. And as a random variable, this function n sub ne of AB is a random variable from omega to positive integers, union 0. Right? Because this function for any interval, for every little n, this function is a function for every point omega here. You compute this, that's a number. Number is 0, 1, 2, whatever. Right? So it's a random variable taking values which are positive integers. Such a thing is called a point random variable. It's also a measure as a function of this interval, and it's called a point process. So in other words, this is a measure. N sub n of E is a measure from B omega when omega is real. For every omega from B of R to n union 0 is a measure. And as a function of omega, it's a random variable. Such a thing is called a point process. Okay, so this n is a point process. And one would like to know, as n goes to infinity, this limit, what is its nature? What kind of point process is it? That's what one is interested in. Point processes are nothing but random measures. You can think of it as random distribution function, whichever. I mean, there are different ways of looking at it. Once you have a measure, you can uniquely associate a distribution function, so you can think of it like that by normalizing something, and so on and so forth. Therefore, one is interested in this process, what it is. So here are the conjectures related to this. So this is a local question. And here are the conjectures. So I'll erase this part of it. Just remember the band matrix. So we have the band matrix H, N, W of omega. This is the random band matrix. Bandwidth W. And this function we are constructing n sub n E associated with the point E omega of an interval AB. This is a random variable if I think of it as a function of omega. So the conjectures are if you look at the limit, suppose it goes to some x E omega of AB. Let me assume that you have a limit. Okay. Then when W is n to the power alpha, with alpha bigger than half and 1 to 1, these random variables x e omega AB and x e omega of CD, when AB and CD are even disjoint, are correlated. Correlated means the covariance is non-zero. The statement I'm making, so that it's here, is much more than this. One gives a conjecture is much more than this. It gives an explicit density for the correlation functions of the numbers here, of the points here. So point process, remember. So the number of points here are say lambda 1 to lambda n, then the correlation of those has the exact density. That is the conjecture. And when alpha is smaller than half and positive, actually it's also true for This case, provided you have this case, yeah, it's true. Trivially, it's true if it is a diagonal form. Then these random variables of any interval AB is a Poisson random variable. That is, its distribution is a Poisson distribution. And again, these conjectures don't depend on the distribution of the random variables Vij, this collection. Whether they are distributed like Gaussian or some other large class of them, independent of all this, these limits have the same behavior. That's what is called the universality. So when you take Vij to be distributed by normal distribution, whatever limit you get, that's what is expected for anything else for alpha bigger than half. And similarly for alpha smaller than half, you expect it to be a Poisson distribution. And this part of the conjecture, when alpha is 1, was proved, and I think even up to some 5 by 8 or something is proved for some cases, Gaussian cases. That is, you assume Vij to be Gaussian and then proceed to prove it. There's a huge amount of work, all kinds of big shots of work on it, like Manju in IAC, Terence Tao, and so on. Okay. So lots of high-powered people have worked on this. Whereas this part of it, nothing is known. When alpha is positive, nothing is known. So let me tell you what we showed. So our theorem is the following. It's a kind of a convoluted theorem because it's not easy to show. So let me. So first we take a random band matrix Hn W omega, like that. Vij, Vij's are distributed like normal. We only take normal distribution, nothing else. And for this case, our theorem is that given an interval, given E in -2 to 2, no, it's not the way. And let me look at the exact statement. Even though I know the theorem, I should write the statement correctly. Okay. So let alpha be bit smaller than 1 by 7, bigger than or equal to 0. Then given an interval I contained in R, there is a subset omega of I contained in -2 to 2 of full measure, which means that the Levitt measure of omega of I is 4. That is, it's a set of full measure here. So that like that for every E in omega of I, I look at these random variables n sub n E omega of I. Remember, E is coming from here and n is the index of the size of the matrix. And bandwidth W is given by n to the power alpha, where alpha is given by this condition. Then this thing, one, has non-trivial limit points x omega I of E, which are positive. Distributed. And this is the first year. Okay, I'll tell you what is the distribution of the random variable. So here, my x omega I is distributed like a boson with parameter lambda, boson with parameter NSC of E times mod I. What is NSC of E? So we have this semicircle law, right? 2 by pi square root of 1 minus E squared by 4. So take this function. That function at E times I. Take that parameter and take the Poisson distribution of that parameter. So for those of you who don't recall, Poisson with parameter lambda is nothing but so that means that is the probability that x omega E of I takes the value k is given by NSC of E times absolute value of I to the power k by k factorial times e to the minus NSC of E times mod I. That's what this is. So the distribution is given like this. That's what Poisson distribution is. So that's what we've shown. Second statement, every limit point of n sub n e omega of I is possible. Every non-trivial. Let me add non-trivial. If it is trivial, then it cannot be possible. So every non-trivial limit point is a problem. So this is the first theorem in this direction, in this area. Even though it doesn't, ideally the conjecture is that the limit points are all Poisson processes, which means this random variable, this function, almost every omega should be a measure as a function of I, and that should be a Poisson measure. So that's a Poisson process. Okay, the function of the interval is a measure. It's a random variable as a function of omega. That's a Poisson process. That is the ideal conjectures. But we get slightly weaker ones, namely for every interval, we get a random variable that has Poisson limit points. We don't even get that it has a limit. Still, however, this theorem says that if you ever prove that there is a limit, then it has to be Poisson. Okay. I'm pretty sure that by a little bit of jugglery, we should be able to show that in this case, limit points are Poisson processes. Because they have some kind of tightness condition and so on. So this is what we have. This is true for Gaussian.
1/7 is sort of temporary.
No, that's not our work. So this work depends on the work of There are, of course, others. There's a work of Jeff Schenker, who showed that if I take this HNW of omega minus some complex number z, take the inverse of this. This is a self-adjoint, this is a real symmetric matrix. So if you take a number with non-zero complex part, then this difference is not real. So because the eigenvalues are real, it inverse exists. This is an invertible object. So this inverse if you take, and then you take the ijth entry, then that has a decay. So this behaves like, so this goes to 0, like some constant times w to the power some sigma, e to the minus some constant times I minus j to the power w to the power 8 or something. Okay, he proved this estimate. This is hard to prove. It's not very easy to prove this. This is expected value. Actually, he shows that the expected value of this is the power some small number s, depends on s, s smaller than 1. So you have an estimate like this. This bound is proved only for this condition. So that is where the condition comes from. And once you have this, then you can show that these limits of this are infinitely divisible. Once you have a random variable that is infinitely divisible and something more, then you show that it is possible. Infinitely divisible means that random variable, the distribution can be written as, or the Fourier transform of the distribution is a product of n functions for every n, for every k functions for every t. Okay. So there's a definition of infinitely divisible means it's like a factorizing an integer or something. You can write it as a product of things. So every measure, if it is infinitely divisible, it means that you can write it as a convolutional product of something. So which I don't want to describe. So something we do using this condition, this estimate. And that's what this depends on, this theorem. So this we showed for Gaussian distribution. Okay. So currently, we're continuing the work where the statement of the theorem is unclear. I mean, it's not neat to write down, but something like this. So even when this is distributed like a different class of distributions, absolutely continuous measures mu, with some mild conditions on moments and the sizes. For all of them, he had shown this bound. Schenker. For all those things for which this is valid, we can show that this sequence has a subsequence. Whenever you have a subsequence of this, where the index is summable, inverse of the index is summable, then you get something similar to this for that particular subsequence. Okay, for much larger class of distributions. So that work is still being written down. So, but you can extend it to much larger class. But these statements are not neat to write down. And of course, getting any theorem is something in this area. And this work with this theorem that I stated here will appear in Journal of Statistics. Okay, thank you.
Any questions or comments?
So you said that it's still left to prove that the limit is actually a measure. So is that what you said? That the
Causal process. Yeah.
okay,
The ideal thing is that this sequence, you put a dot here, so this is a random measure. This sequence of random measures converges to a random measure, which is a Poisson random measure. The limit itself exists as a Poisson random
so by that you mean that for almost omega. So so the dependence of this guy on I actually.
It becomes a measure as a function of I.
And
There's a notion of Poisson process. Poisson process is nothing but random measure whose for every interval the distributions are Poisson random variables, but they must be independent. That is, you have independent increments. You know a Levy process, right? Oh, you don't know, okay. I keep thinking you're a problem. Yeah. So if you write it in the language of okay, if I take two intervals I and j, which are disjoint, then the corresponding limits, not this, the limits, if I and j are disjoint, then these ones corresponding to I and j are independent. And as a function of I, they are independent random variables. As a function of I, they give you a measure. That is I union j of this is going to be sum of this whenever they are disjoint and so on. And the appropriate properties of a measure almost everywhere. And such a thing is called a Poisson process.
Why does half kind of behave very difficult point?
These are the conjectures by physicists. Physics conjectures are physics conjectures. It's a surprise that they are true actually. But of course, nobody has a conjecture as to what happens at half.
So in the value matrix, the elements are evaluated at zero.
Right.
So if W is n to the power alpha, and alpha is say alpha is half, and n is not a square, then what is V1 and V?
Well, you just take the integer part.
Oh.
See, one is very loose in this statement. Okay. When you say it is n to the power alpha, the order of W is like n to the power alpha. So you can adjust by 1 or 2. So you can take it to the integer. So in these kinds of areas, one is a bit loose in talking. And you don't even write precisely like this. You don't say that I take away the big integer part, but it is understood.
The Hermitian also is a workbook and stuff.
Yes, if you take Hermitian, then these random variables are Bij have
The law is still the semicircle.
yeah, for everything you get a semicircle. Bij is going to be two parts, Bij real plus I times Bij imaginary. So in this case, you have a normal random variable on C2, on C. So it's a so it's a random variable, e to the minus a square plus y square by 2 with appropriate number. Right?
This one. If you take a real semicircle group and take a neointegral, look at the people, I'm looking at orthogonal as a key point. So if I take some collection which goes up to infinity, then will I still get some kind of bigness type of loss?
I have no idea. I've left semicircle groups in my childhood. I'm sorry, I've not kept track of.
No, I'm just,
I have absolutely no clue. Something I want to say. By the way, the only thing that is close to your subject is that the Riemann zeta function, if you look at the zeros on the critical line, the distribution of that is supposed to be like the distribution of the case when of this limit when alpha is 1. Gaussian orthogonal. That's what it is. There is a conjecture, but I think if you periodic zeta function, it's proved by Sarnath.
yeah, the cards are not. But that
Cards
can
and-
also look at finite field. Then we look at what's called the monotony. That you can divide it into other infinite terms,
Mhm.
symplectic terms,
Okay.
and then ask for that behavior also. Anyway, I don't understand this.
Yeah, there are three different limiting laws for local states.
No, but sorry, but I'm just saying going back to the Wigner. So
Wigner, I think, would be the same.
there is only one limiting behavior. There is nothing like symplectic behavior.
I don't think so, but I'm not sure of this. I don't think there is. Because it is just the counting function, right? It is just one measure. Whereas in the case of local statistics, there is a difference because the number of initial random variables are more than n squared, roughly like n squared. Okay.
Okay, so any questions? I mean, Ajit Iqbal Singh was there, but she left. Okay, so then let's thank the speaker.